In this video, I'm going to be talking about the 4 big fat topics of differential equations that you need to know. This is kind of an introduction video. I'm going to be talking about what is a differential equation, right? You're taking the class. What in the world is even a differential equation? What is an ordinary differential equation? And for clarity's sake, DE for the rest of this video, if I ever write it down, just means differential equation. So an ODE stands for ordinary differential equation. PDE stands for partial differential equation. The order of your differential equation also matters, and you'll also, or not you, what am I talking about? I will also talk about linear versus non-linear differential equations. Now, before you continue on this video, I suggest you give yourself a pat on the back and give yourself some self-love because you passed Calculus 3. Or Calculus 2 if your call doesn't require Calculus 3 for differential equations. But give yourself a pat on the back. You made it through pretty tough classes, I'd say. Now you're on to an even tougher class. So I'm smiling right now. I don't have a face cam because my computer just doesn't have a built-in camera. But that's besides the point. Let's talk about what is a differential equation. Okay? What even is a differential equation? You're taking the class. You don't even know what it is. Well, I'll show you. A differential equation is simply any equation that involves a derivative. So dy over dx is equal to 1, right? This has a derivative. This is a differential equation. What does differential in DE stand for? A derivative, right? You're taking some, whatever. I'm not going to go into the nitty-gritty English of it, but this right here, dy over dx is equal to 1. This is an example of a differential equation. Another example of a differential equation is y double prime plus y plus 3 is equal to, I don't know, x. Okay? This is also a differential equation. Another example of a differential equation is also partial y. Sorry, let's say partial z over partial y plus partial z over partial x is equal to 0. Okay, this is an example of differential equation as well. And at the beginning of this video, I talked about PDEs. I'll get into that later, but this is an example of a partial differential equation. Now, I'm going to introduce a couple other things as well, especially notation-wise, so you guys can actually understand what I'm writing. But basically, dy over dx stands for a first-order derivative, which means you're just taking the derivative of some function a single time. If you want to represent this as a second-order derivative, you would put the square next to the d, not next to the y, next to the d, and a square in front of the x in this case. Well, technically it's dx, but this right here stands for a second-order derivative, which means you're just taking the derivative of some function 2 times. Okay? Now, why is this important to know? Well, first off, again, it's notation as well. But you'll see later in the video why this is important to know, right? To understand these little numbers here, what do they stand for? Now, also another thing to look out for is y double prime. These two mean the same thing. Okay? Y is our function, correct? Y is equal to f of x. Maybe you haven't seen this too much. Maybe in your classes you mostly saw f of x. Okay, in your calculus classes, I think a lot of teachers use f of x instead of y. They equal the same thing actually. Y is a function, just like f of x is a function. And both of these are dependent on x. So in this case, y is the dependent variable, and x is the independent variable. Now, if you've noticed this as well, if you ever take a derivative, the value, the variable at the top of your derivative using Leibniz notation, this dy over dx is Leibniz notation. If you see a variable at the top, this stands for the dependent variable. I was looking for the word. And the variable at the bottom stands for the independent variable. Now, this is also important to know, because I'll cover this later in the video. Now, another way to write this instead of y double prime is also f double prime of x, right? Maybe you saw this in Calculus 1. Maybe you even saw this in, you probably see it less in Calculus 3 because you're mostly taking partial derivatives. But this right here is a little bit of a refresher on the notation, okay? Both of these, all 3 of these, not both of these. Both of these means there's 2 things. But all 3 of these mean the same exact thing. Just a second derivative with your function y, or f of x. Now, the reason why I point this out is because you're going to see differential equations of all different kinds, right? Y double prime, minus 3y prime plus y is equal to 0. This is an example differential equation. And if I were to use the little logic I did previously, right, y stands for some function. And let's move this up so it's not all cluttered together. But y stands for some function. D squared y over dx squared stands for the second derivative of the function y. And right here we have 2 primes, which means this is the second derivative. 3 dy over dx. This stands for the first derivative, and since there's a single prime on the y, this is just the first derivative function plus y. And since y is just by itself, I can just represent it as y is equal to 0. These two things equal the same thing. And if I were to use f of x, I think differential equations uses f of x just slightly less. My class uses it a little less, but it would be f of x double prime, right, minus 3f prime of x plus y is equal to 0. Right? All these guys mean the same exact thing. Now, before I continue on this video, maybe you see a little bit of lag right now. It's because I'm running a program on my computer. I'm doing my homework in this moment. I'm actually doing, I don't know, maybe I shouldn't share this because one of you guys are going to take my ideas from my paper. And it's also going to make the video longer to make less engagement. Or less click-through rate. That's bad. Actually, click-through rate, not that big of a deal. I'm making these videos for fun. I don't know. Maybe I'll get a lot of subscribers one day. That'd be pretty nice. That'd be pretty nice. But basically why I'm lagging right now is because I'm running a program that's very intensive. I'm doing things related to quantum computing, and it requires a lot of computing power, and this is making my computer lag. So if the video is laggy, that's a little warning. Now, let's move on to the next topic. Ordinary differential equation versus partial differential equations. So in the case of these two equations here, I want you to take a guess which is the ordinary, which is the partial, using your knowledge from Calculus 3. You haven't taken Calculus 3? That's fine, I'm about to explain it. But now that you have hopefully done what I said to do, an ordinary differential equation is a differential equation where there's only one independent variable. A partial differential equation has more than one independent. I'll just write down indep var. Okay, so a partial differential equation has more than one independent variable. Usually, if you see this partial derivative sign, which I have so stupidly called delta in my Calculus 3 videos, if you've watched those, you know what I'm talking about. I call these delta. It's just partial, just called partial. It is not the delta Greek letter. But basically, if you see delta, it's pretty safe to assume, you've given standard notation that, sorry, I said delta again. If you see this partial symbol, it's pretty safe to assume this is a partial differential equation with more than one independent variable. In this case, remember, whatever's in the denominator, remember what I said previously, whatever's in the denominator is the independent variable. Whatever's in the numerator, or at the top of your derivative in Leibniz notation, is your dependent variable. Okay, so the bottom is the independence, the top is the dependence. And z right here is the same. It's the same two top variables. So z is just our one dependent variable. But we have two different independent variables, x and y. And this right here is called a partial differential equation when you have more than one independent variable in your problem. But in the case where you see y with the primes, right? If you see f double prime, this is pretty safe to assume this is just an ordinary differential equation. Now, if you don't see this little prime symbol here, right? If you have Leibniz notation, for example, dy over dx squared right here plus 3 dy over dx maybe is equal to x minus 2. This is an example here. In this case, you only have one independent variable, right? You have x on both the denominators in Leibniz notation, and both of them are the same variable. X is the same variable, and y is the same variable top. This is an ordinary differential equation. So remember, ordinary differential equation, right? You have one independent variable, and that's pretty it's pretty easy to tell based on the denominator in the Leibniz notation, or just based on the d. Okay, and a partial differential equation. Most of the time, you're going to see not all the time actually. That's why I'm saying most of the time, but not all the time. But most of the time, you're going to see the partial derivative sign. And you're also going to see more than one independent variable inside of the denominators of these Leibniz notation derivatives, x and y. Next topic, order of your differential equation. So right here are 4 different examples of differential equations, right? And I want you to determine I'm going to talk about, and also you could probably determine them before, but what is the order of the differential equation? You can already guess that order stands for the amount of derivatives you took, right? So if you took 2 derivatives, this would be called a second order derivative, right? So in this case, right here, we have d squared y over dx squared. This right here stands for the second derivative, correct? Of our function y, second derivative of our function y. And this right here stands for the first derivative of our function y. And actually just our function y by itself stands for the 0th derivative. So we didn't take any derivatives. This stands for the 0th derivative. Okay? Now, here's the thing about the order of a differential equation. The entire differential equation itself is this guy, correct? What is the order of this entire differential equation? Well, the order of the entire thing, not just the individual parts, of this first one is a second order differential equation. Now, why is that? Well, the reason why this right here is a second order differential equation is because the second derivative overpowers everything else. And not overpower as in numerically, but it overpowers the classification of the differential equation. So this right here is the second order differential equation because the highest order derivative you find inside of the entire equation is the second order derivative. So the entire thing is a second order differential equation. The highest order derivative in the equation is the order of your entire differential equation. Soak that in. Soak that sentence in. Okay. Now, how about this guy right here? How about this guy? Well, we have a 0th order derivative. This is just the original function. But we have a first order derivative here. And we have, well, we don't have the function y here. We just simply have 1 over x. So this entire guy right here, what is the order of the derivative? The highest order derivative you find in the entire differential equation is the first order, right? You just took a derivative once. There's no second order derivative here, and there's no third order derivative, fourth order, whatever. Okay, there's none of that. The highest order derivative in this entire equation is just simply the first order. Therefore, the classification of this entire differential equation is a first order differential equation. Now, how about this guy right here? Is this our first or second order differential equation? This one is a little bit more challenging. And the reason why is because of the square here. Now, let me explain. Actually, let's write down the answer for this, okay? We have a 0th order derivative here, so we're not taking any derivative. But we only have a first order derivative here. What does the square stand for? How is this any different than this? Okay, if you already know the answer, pat yourself on the back. But the reason why these two are different is because this right here stands for taking the derivative twice. So if I were to draw an arrow, if I were to expand this guy right here, it'd be d over dx times d over dx times y, right? Or function y or f of x. It can be replaceable. Y and f of x are interchangeable. But this right here is essentially this, okay? So you take the derivative of y, and then you take the derivative of y. But the reason why this is different is because when I write it out, it is d over dx times y times d over dx times y, right? Or if I were to write this down in another way, it'd be dy over dx times dy over dx. So in the case of this square right here, you're simply multiplying the functions of the first order derivatives together. The first order, keep that in mind. You're just multiplying the function of the first order derivative by itself. Okay? So dy over dx squared is multiplying the first order derivative by itself. But d squared y over dx squared is taking the derivative twice of your function y. So this is a very key distinction here. Okay, this right here is taking two derivatives. This right here is multiplying two first order derivatives. So keep that in mind. Therefore, this guy right here is a, redo that. Okay, I guess I can't redo. This right here is a first order differential equation since we are not taking a second order derivative here. Okay, the largest derivative you're finding this entire equation, simply the first order. And this would be the same thing if this was to the cube, to the fourth, to the fifth, right? You still only have a first order derivative in this entire equation. Okay, what about this next section right here? All right, take a look at this. Different notation. What's the order of this differential equation? Well, we have y double prime times y. Just the second order derivative times the original function, the 0th order derivative, plus 1 over x. So currently we have a second order derivative, that's our highest, but this is equal to y triple prime. Okay, well, since this is a second order derivative here, and we have a third order derivative, what's the order of this entire differential equation? Well, the order of this entire differential equation is a third order differential equation because the highest derivative, the highest order of a derivative you found in the entire equation is a third order derivative with these three, signifying these three little prime guys right here. Okay, so remember, the order of a differential equation is determined by the highest order derivative in the equation. Last topic, and I saved the last topic, linear and nonlinear, because this one is the hardest one to understand. And, you know, more comes with practice, the better you'll get at this, of course, because you're going to be using this the entire semester, right? There's going to be different techniques to solving differential equations, and knowing if it's nonlinear and linear would help a lot. So, let's talk about linear versus nonlinear differential equations. How can we tell if a differential equation is linear or nonlinear? Well, there's two big things that you typically look for. One of them is that one of your derivatives is not multiplied by the function y. If this is the case, then your function is automatically nonlinear. Okay? So y cannot be multiplied by any of its derivatives, or any of its derivatives multiplied by other derivatives. So, for example, fine, y double prime times y, right? If you saw the first derivative times the second derivative in any of your differential equations, this is automatically nonlinear. Okay? All right. How about another thing, right? So let's already classify this as nonlinear. Let's write down NL. Okay? Another thing is that y has to be to the power of 1. And a derivative of y also has to be, so this is y prime, also has to be to the power of 1. It cannot be squared. If any of its derivatives, if any derivative of y or any function of y is being squared or cubed or just anything other than the power of 1, it's automatically nonlinear. So I've already given you an example of that. Right? So remember two conditions. Functions can't be multiplied by each other, right? Derivatives can't be multiplied by each other. And also, they have to be to the first power. So in this case right here, we have a nonlinear differential equation because y is being squared. Okay? Since y is being squared, or even if this was being squared as well, right? This would be nonlinear. Okay? If any derivative of y, or even the function y itself, is being squared, cubed, whatever, quarticed, okay? It is nonlinear. All right. Now, how about this? Well, this isn't to the first power. Okay? Since y right here is not to the first power, it's being put into a sine function, this is also nonlinear. All right? So sine of y is nonlinear. Plus y prime, doesn't matter what the entire other thing is. If even one component is nonlinear, the entire differential equation is nonlinear. How about this right here? Well, y is being put to the power of e. This right here is also nonlinear because y is not to the power of 1. Y has to be to the power of 1, or any of its derivatives have to be to the power of 1. Since y is being put into an exponential, this is also nonlinear. Okay, how about this? Right? Well, y is to the power of 1 in this case, right? Just by itself. We have x. That's completely fine. Right? And we have y prime double prime squared. Remember what I said about none of the derivatives or y itself being put to anything else other than the power of 1? Well, this right here is to the power of 2. Okay? Y double prime, the second derivative of y, is being put to the power of 2. It's not to the power of 1. So this is nonlinear. Okay. All right, how about this right here? This right here is a little bit more subtle, but if I were to manipulate this to get y double prime minus x over y, right? All I did was subtract x over y onto both sides of the equation. We have y double prime minus x over y. Well, it's y to the power of 1. Is it? Well, remember, we can also rewrite this equation. This is a little sloppy, sorry for the little clutter. It's just, there's not much space. But y double prime minus x times y to the power of negative 1 is also equivalent to this equation here, correct? Right? Y to the power of negative 1 is simply 1 over y. So it's 1 over y. And x times 1 over y is x over y, right? So y to the power of negative 1 in this case is not 1. Y is not being put to the power of 1. So this right here is this equation. Let's actually undo everything instead of erasing and almost hitting something. But this equation right here is nonlinear. Everything I've talked about is nonlinear. Are we going to see any linear examples? Jitty, you're an idiot. Okay, don't call me that. But these two, let's take a look at them, okay? Is y, or any of its derivatives, multiplied by another derivative of y or a function of y? Okay, so for example, this right here, this derivative of y is being multiplied by the function of y. Well, this right here is just a lone first derivative y by itself, plus 3y is equal to 0. So we meet this condition. Ooh, check, put a check there. Because none of its derivatives are multiplied by another variable, another function of y. Okay? Okay, how about the second condition? Everything to the first power. Well, this first derivative is to the first power. Oh, phew. This first derivative is to the first power. So, plus 3y. Y right here is also to the first power. You don't see a square, you don't see a cubed here. So this guy right here meets both the conditions, meets both the big conditions of linearity. So this right here is linear. How about this equation right here? Well, we have x squared. I haven't talked about this yet, right? I'm scratching your head a little bit. Is this linear? Is this non-linear? Well, x squared is not y. Okay, x squared is just x squared. All right, this is just the independent. This right here is just simply the independent variable by itself. So y double prime, since y double prime is not multiplied by another one of its derivatives or the original function, this right here is good. And same for e to the x to the power, e to x times y prime is good as well. Okay, this right here is good. It meets the condition of linearity. Y isn't multiplied by itself, okay, or any of its other derivatives. Just e to the x. That is not the function y. Plus cosine of x. Well, since x is a independent variable, it can be inside of cosine. Okay, all we really care about is y, or f of x, or dy over dx, right? Whatever notation you're using. All we care about is our function. We don't care about the independent variable. So cosine of x, we're good. This is still linear based off the conditions we checked. How about the square condition, okay, or the cube condition? Every y and all its derivatives need to be to the power of 1. Well, y double prime is to the power of 1, right? We don't see little parentheses with a square around it. And y prime is also still to the power of 1, right? And keep in mind this is a prime symbol, not 1. So we meet that condition too, right? So since none of the values y and its constituents are being multiplied by the function y or any of its derivatives, then, and also since it's not squared, then this is linear. Boom, boom, boom. Maybe I should change the color of this because the L looks a little bit like a check mark. So we've talked about linear and nonlinear, and hopefully I showed you enough examples for you to understand this. I know this video has been quite long, but it's an introduction to a lot of things in differential equations. Now, I want to point out one thing that you need to watch out for, and it's this. Right? Remember previously I mentioned these two are not equivalent? Well, this right here is equivalent to y double prime, right? Y double prime squared. So y double prime is, sorry, not y double prime, y single prime squared, right? Y single prime is the first order derivative. This stands for the first order derivative. And if you square y prime, right, you're not taking the second derivative, you're simply squaring the function, as I covered before. You're squaring the first order derivative, right? You're not taking the second order derivative. So this right here, dy over dx squared, if you see this inside of a differential equation, like for example, plus, let's say 5y is equal to x, right? This differential equation right here is nonlinear. And the reason why is because your derivative is being squared. Now, if this was different, if this was, and actually let's copy and paste it so you can look at both examples. But if this was, let's say, oh, I'm running out of space. Oh. If this was d squared y over dx squared, this is simply second order derivative, okay? You're not taking any squares of any derivatives. This right here is just stands for y double prime. This is completely fine. Y double prime is not being squared or cubed, right? It's just the second order derivative. But in this case, it's the first order derivative being squared. So this is nonlinear, and this is linear. So keep that in mind, okay? Squaring a derivative is completely different than taking the second order derivative. Notations, you have to watch it for that notation detail. But, no, this has been a long video, so if you stuck through this, or maybe you skipped through all the timestamps and you just happened to stumble across this outro, I hope this video helped. And if you have any questions, put it on in the comment section. If you found this video helpful, consider subscribing and liking the video. Thanks for watching.